Welcome back, everybody, to INE's CCIE Data Center Nexus switching class. In our next section, we're going to talk about multicast and how it integrates with the virtual port channel or VPC feature that we've been talking about up to this point. Now, before we get into any of the technical details of the differences between multicast in a regular Layer 2 and Layer 2 environment and how it works over the VPC, I actually want to start first on the command line with the example, and we're going to look at just some basic multicast flows and then kind of work back from there and see what are the changes of multicast working over VPCs as opposed to just a regular Layer 2 switching or a Layer 3 multicast routed environment. So if we take a look at the topology that we have here, I made some changes from our previous example where we have the 7Ks at the top. These are currently the only two devices that are running VPC. So we have our VPC domain. Specifically in this case, we have VPC domain number 7. We have the peer keep alive link that is between the M ports, and then we have the peer link that is on the F ports. I now also have two VPCs. There is VPC 51 that is going down to the first 5K, and there is VPC 52 that is going down to the second 5K. So in this case, it is no longer a back-to-back VPC. It's a regular VPC where we have multiple member ports. From the downstream switches perspective, the 5Ks, we have the single port channel on the 5Ks upstream to the 7Ks, but on the reverse side, we have two separate VPCs. So it's not back-to-back. This is a regular VPC design. Okay. Additionally, from the 5Ks downstream, I do not have these interconnections where we have the basically active FEX. Instead, what I have here is just the single connectivity of the ports. But we don't have the cross connections between the 5Ks and the 2Ks, just temporarily for the point to show how the single traffic flow is going to work when basically we only have one option to go upstream towards the VPC peers. Now again, normally from a design point of view, this is not what you would want to have because these FEXs are basically now orphan ports that are hanging off of the upstream VPC peers. So ideally we would want them to be dual connected, but in this case they only have one upstream parent. Now additionally, we have a couple different devices we're going to be testing this from the actual end hosts. On the first fabric extender, we have router 3, and we also have server 1 that is dual attached. This is the one that has the two 10 gig NICs. It's got the 10 gig converged network adapter. Then on the second fabric extender, we have router 2, and we also have server 3. Server 3 in this case has two 1 gig links that are bound together in a port channel, so we have a 2 gig channel. Now, from the previous example, we were talking about the first hop redundancy protocols and how we deal with HSRP, VRRP, and the GLBP changes. So we have two different Layer 3 segments. We have VLAN 10, where VLAN 10 is the subnet 10.0.0.0/24, and we have VLAN 20, that is the subnet 20.0.0.0/24. Now, from the perspective of multicast, what we're going to look at first is flows that are happening within the same broadcast domain. So where we have a sender and a receiver both in the same VLAN, and we're forwarding the traffic over the VPC. And then we're going to look at some routed designs when we have Layer 3 multicast routing, so we have to go through multiple Layer 3 hops, which means that we're going to be running PIM. And we'll also see that VPCs do have some limitations as to the multicast applications that they can use. So they do not support source-specific multicast in the current releases. You have to be running any source multicast either with PIM sparse mode with a rendezvous point, or you could be running PIM sparse mode in bidirectional mode for your any-to-any trees, if your senders are both senders and receivers at the same time, which would be a more common design in like financial environments with high-frequency trading, when the end hosts are both the receivers and the senders of the stock ticker applications. That would be typical for a data center environment if you're doing any type of HFT. So here what we're going to do is on the routers, we can make them both multicast senders and receivers just by doing basic IP-IGMP join on the interface and then doing some pings. But also on the actual servers that we have with that JPerf application that I was generating the TCP frames with, we can also use that to generate some UDP flows. where we have the UDP server that is basically going to be the receiver of the multicast feed. We can have it generate IGMP report messages. Then the multicast sender is going to be actually sending the UDP feed out, and we're going to look at what is the result of this from the case of the layer 2 network. Now, traditionally, layer 2 multicast network has been pretty much plug and play. That we know that when we deal with taking traffic that needs to go to more than one port at the same time, the layer 2 switches need to optimize this so that the multicast traffic is not treated as broadcast. So I don't want a multicast feed to come in on one of my uplinks and then me forward those downstream on every single port, the same as I would a layer 2 broadcast. So even if the switches are just doing layer 2, they do need to have some layer 3 multicast intelligence, and that's going to come in the form of IGMP snooping. Now, in the case of Nexus, IGMP snooping works a little bit differently than the way it does in Catalyst iOS. Then in Catalyst iOS, we're looking for the specific layer 2 multicast format for multicast MAC addresses, and based on where the IGMP report message is going to, the switch is going to figure out what is the particular multicast group that the receiver is trying to get. Now, if you know anything about the specifics of how multicast layer 3 addressing works versus layer 2, the layer 2 MAC addresses that correspond to multicast actually overlap to multiple layer 3 multicast groups. So this means that I could have a single multicast MAC address that there could be multiple senders with different group addresses that are overlapping to. So in order to solve this problem, the way that Nexus deals with IGMP snooping is just to look in the actual layer 3 payload of the IGMP message. So we're actually doing layer 2 multicast forwarding based on the layer 3 information. So that's then going to be our first step here. Let's go to the end servers here. This is going to be between server 1 and server 3. And the first thing I want to do is to just generate an IGMP report message, or the IGMP join. So under the traffic generation application here, I'm going to say that I want to be the UDP client. So we're going to be running UDP as opposed to TCP here, because multicast is going to be UDP based. And the specific host address that I want to be using is going to be any multicast group. Let's say 225. Let's say 225.555. And actually, we are going to be the server here. Okay, this is kind of backwards how this application works. There's the client and the server. The server is actually the receiver of the feed, so it means that it's the multicast receiver generating the IGMP report. The client is actually the multicast sender, so that would be like your media server or whatever your multicast feed application is. So this is UDP. The host address is 225.555. This is going to be what I send the report for. Okay, now this particular server, server 1, is physically located on Nexus 2K1. So it's over here. This means that the IGMP report message, which is the IGMP join for the star, G, so I don't care what the source is, I'm just trying to listen for that particular group. It goes on to the layer 2 segment, which in this case is the VLAN 10. And if we go to Nexus 5K1, and we look at the show IP IGMP snooping groups, we see that particular address, 225.555. We now know that if we receive packets for this, it's going to have to go out port channel 10. Where port channel 10 here, this is the actual access segment that's going down to that server that is in VLAN 10. Okay, so we know that the first hop into the layer 2 network does know that someone is trying to actually receive that multicast traffic. Now, in order to get there end to end, we're going to be sending the traffic between the servers. So it's going to be coming from server 3. It's going to go to 5K2. 5K2 is going to have to send this up to 7K1, or actually 7K1-2. 7K12 is going to need to forward it some direction down here in order to get to the receiver. Now, we'll see that this is going to be some of the behavioral change here. We need to think about when the packets come in, are we going to send them out just the VPC member ports, or are we going to send them also out the peer link? We saw in the other data flows up to this point, we want to try to avoid using the peer link for the data plane, use the peer link ideally just for the control plane synchronization, because the peer link's bandwidth is going to be much smaller than the aggregate of all the VPC members. So what we also need to do here is actually turn on multicast functionality on the 7Ks, which is our layer 3, layer 2 boundary. So it's not technically going to work just as a flat layer 2 network with IGMP snooping, because we need someone to act as the IGMP courier to actually build the basic layer 2 tree. So on the 7Ks, what I need to do here is go to global config and turn PIM on. So this is for protocol independent multicast. We're going to be running PIM in sparse mode. I then need to go to my VLAN interfaces and just turn PIM on, IP PIM sparse. Now, we're not actually doing routing yet, so I don't necessarily need to define a rendezvous point. I just basically need to turn the feature on, so we start to listen for the IGMP report messages, and then we can build the basic layer 2 multicast tree. So we'll say IP PIM sparse at these VLAN interfaces. Okay, if we now go to this other 7K and let's look at the show IP IGMP snooping groups, we now see that there is a receiver out port channel 51, which is the VPC member port going down to 5K1, says they're trying to receive the multicast group 225.555. Okay, now again, as I mentioned, the other Catalyst iOS platforms, the way that they deal with this is by having a separate layer 2 multicast CAM table, or a multicast MAC address table. In the case of Nexus, it does not work that way. We're going to be doing layer 2 multicast based on layer 3 forwarding. So if we look at the show MAC address table dynamic, in regular Catalyst iOS, you would normally have a multicast option here that shows you your conversion between the layer 3 multicast destination and the layer 2 MAC address. But in this case, we're just doing native layer 3 forwarding. So we're going to look at the IGMP information. We're also going to look at the regular multicast routing table. Okay, let's also now look at 7K1-2, which is the other VPC peer. Let's look at the show IP IGMP snooping groups. This switch likewise knows that there is some receiver, we don't know who it is, but there's some receiver that's located downstream out port channel 51 that is trying to receive 225.555. Okay, if we go now to 5K2 and likewise look at show IP IGMP snooping groups, we see right now we don't know about the receiver because we didn't actually start to build the full tree. So we're not going to know about this information until we actually need it. Okay, now let's go to the sender of the multicast traffic. So on server 3, and if we actually, what I should take a look at here first is the IP config. Right now these devices are in the same IP subnet. Okay, they're both in VLAN 10. One server has 10.0.0.12, has, no, actually this one, E210 has a rate of about 1 million bits per second, and then also E213. Okay, let's actually bump up the feed a little bit higher so we can differentiate between these links, because you can see just based on the control plane, there is a bunch of basic exchange that's going on between the ports. So I want to be able to differentiate clearly in the data plane exactly where the multicast is forwarding. So let's stop this and let's say that we're going to bump it up to, let's say 100 megabits per second. Okay, so now the feed is 100 meg. If we go to the receiving server, we should still be getting this here. Okay, so now it's coming in at 100 meg. And let's look at this show command again. So it's actually two of these interfaces. It's Ethernet 2/9. We can see the output right there. And it's Ethernet 2/14. If we take a look back at our topology, so it's E29 and E214, Specifically, these are one of the members of the peer link and one of the members of the VPC member link. So the multicast feed is coming in here and is going out not only the VPC member interface as we would assume that it would, but it's also going out the peer link in the data plane. So this is the first major change that we need to think about in the design of VPCs, is that when there is a receiver that is behind one of the member ports of the VPC, the multicast flow will be always sent across the peer link. Now, the reason that that is a requirement is that the receiving switch of the feed cannot guarantee that the remote VPC peer does not have orphan ports that are trying to receive the multicast feed. Now, we know with regular unicast communication, it's pretty easy for us to figure out where are the sources and where are the destinations, because we know all the source MAC addresses and the destination MAC addresses based on our normal flooding of frames. So when ARP comes in, it's going to the all F address for broadcast. Based on the ARP coming in, I now know what the source MAC address is of the sender. Okay, the ARP goes out, the reply comes back in. I now know where the MAC address of the receiver is. So if I have unicast communication between those two hosts, I know exactly where to switch the frame between the ports. But unfortunately with multicast, we cannot guarantee where the receivers are going to be. So in the case of VPC, again, when the multicast receiver is on a VPC member port, the multicast feed is going to go down the member port and additionally across the peer link. Now, once the remote neighbor receives the multicast feed in the peer link, we will respect the VPC check rule that says packets coming in the peer link cannot be forwarded out a VPC member port unless the remote VPC peer has that member port disabled. So again, the goal is to make sure that we're not causing a layer 2 loop. So if we look back at our topology here, when 7K12 is receiving the multicast feed in, it already knows that there's a receiver down here on the member port, and that was based on our IGMP snooping. But unfortunately, it cannot guarantee that there is not an orphan that is somewhere behind 7K1-1 that likewise does not want to receive the feed. So when 7K1 receives the multicast, it could potentially go out towards the orphan port, but it will not go back out the VPC member ports. So even though it is going to be coming in the peer link, it is not going to be going continually downstream from the remote peer's perspective. And we should be able to see this if we go to 7K1, and let's look specifically at those ports, which are E2/1 to 6. And we should be able to use basically the same show command here and just change what the port numbers are. So if we show interface E2/1 to 6, and let's say another pipe, no more. And let's run this command a couple times. So I want to look at, in this case, what are the input and the output rates. Here we have Ethernet 2/1, where the average input rate is about 85 megabits per second. So that has to be where our multicast feed is coming in. Okay, so it's not exactly 100 meg, it's a little bit less than that. E2/1, if we look back at our diagram, this is the peer link. So it's a member port of the peer link. So that's showing us we are receiving the multicast feed in the peer link. When we look at the outgoing ports, though, the output rates are very low. So based on this, we can tell that we're not continuing to forward the multicast feed on. So we are receiving it, but we're not continuing to send it because the only receivers are located on the VPC member ports, and that would be a violation of the VPC check to receive packets in the peer link and then continue to send them out the member ports. Okay, this is going to bring us then to our first point about the change in the multicast. When the receiver is reachable via the VPC member link, the IGMP report information is automatically going to be synchronized for us. Since we're already running Cisco Fabric services over Ethernet to synchronize the control plane for the consistency check, For the MAC address table, for the ARP table, we're also going to use this to synchronize the IHMP report messages. So if one of the switches receives a join, or the report more specifically, it is going to tell the other VPC peer that now I have a receiver for this particular group. Now normally, when the receiver is reachable via the downstream link, in regular multicast forwarding rules, let's say that we have two routers on the LAN segment and they're going to be forwarding the multicast feed downstream. Normally only one of them is going to be forwarding. And specifically in the case of PIM, this is known as the PIM assert winner. Normally the assert winner is going to be the device that has the lowest upstream IGP cost to the sending segment. Now in this case, when we're dealing with the layer 2 LAN, since the sender is directly connected, essentially both of the peers have the same assert metric back to the source. So there is kind of a tie-breaking mechanism. We don't need to get into the details of PIM and actually how the control plane deals with this. But normally, under most cases, there's going to be only one sender that continues to forward the traffic. Now in VPC, this is going to change. The primary VPC peer is going to be the one that is in charge of forwarding the traffic towards the peer link and towards the member ports. So depending on where the feed is coming in, and this is going to assume that it's coming from upstream, like coming from the upstream core, and then going down to a receiver that is actually on the member ports, it's going to be the primary VPC peer that is in charge of doing the forwarding. Regardless of whether they are the assert winner or not, that's going to be one of the roles that the primary is going to take the place of. Okay, but another change here is that on the secondary, we are going to be receiving the multicast traffic in. We're receiving that in on the peer link. Then we can continue to forward it on the orphan ports. So this means that either these ports were previously VPC members, but there was a failure on the remote peer, or they were single attached hosts to begin with, or it could be switches or routers, something that's not dual attached to the VPC domain. So this is the exception to the VPC, or excuse me, it is not the exception to the VPC check rule. So the feed is coming in on the peer link. We're saying packets received on the peer link cannot forward out the member ports because that would break our basic loop prevention mechanisms in the data plane. Now from a design point of view, what this means is that the bandwidth budget of the peer link does need to be considered if we have multicast receivers in the data center. So if there's applications that are sending large multicast feeds and then they're going to the receivers there on the LAN, that traffic is going to be sent over the peer link, or actually in the case that the multicast sender is behind the VPC member ports as well. It's actually going to be bidirectionally. So if multicast is used basically at all, it is going to be sent over the peer link in all cases. So we do need to take that into account for the bandwidth budget. So if you were using the platform, let's say for example, for like triple play type services for like a cable content provider or something similar, where you're doing IPTV and your multicast is used for that HD video stream, then you would need to take into account that each of the streams will have to be replicated over the VPC peer link. So where in this case we have two 10 gig Ethernet links, depending on how large the feeds are, you may need to add additional links on the peer link to take into account this forwarding for the multicast traffic. Now the next case is going to be when the sender is behind the VPC. Okay, it's actually both cases that we have here because we're doing switching LAN to LAN. Okay, but when the sender is reachable via the VPC member, both of the peers are going to be acting as what is known as the PIM designated router. Now the PIM designated router has the role of informing the rendezvous point that a new sender has come onto the network. The way that it does that specifically is with the PIM register message. So normally the designated router is going to be sending the unicast register message to the rendezvous point, basically telling the rendezvous point that I have this new S, G, or this source that is sending to this specific group. Now the potential problem we run into then with VPCs is we cannot predict in advance, based on the Ether channel load balancing mechanism, which of the VPC peers is actually going to receive the feed first and then have to send the registration to the rendezvous point. So in order to fix this, basically what we do is make both of the VPCs act as if they were the PIM designated routers. And this is called either the dual DR or the proxy DR for PIM. So essentially both of the VPC peers are maintaining this same role. So this does mean that there can be some redundancies in the multicast traffic. Usually it's going to end up working itself out because when we have the traffic go to the receivers, we have that restriction of the VPC check. So as it goes across the peer link, once it gets to the other side, then the traffic is not going to be forwarded back out member ports. So we don't end up having loops in the multicast traffic. Okay, it just means that both of them are going to have to maintain more information in the control plane. Now, the idea behind this is that it's going to allow either the VPC primary or the secondary to receive the traffic and then forward it upstream without necessarily having to cross the VPC peer link. Okay, so it really depends on where the receiver is, whether this traffic is going to need to go across there or not.